So now we know covariance and we know variance, so we can calculate the, we can capture the spread of the whole data set. So what we do is we use a covariance matrix. What is a covariance matrix? Let me just show you. I think I don't. Do I need this? Now I have formula to calculate the covariance, right? We calculate mean, then we do the differences from mean for two features, and we do a sum of them. We divide it by the number of examples. Doesn't care about this -1. This -1 is just for statistical purpose. If we -1, we call it population covariance or population variance. If we don't -1, it is kind of sample variance. It's a statistical issue. Don't care about that. So if x equal to y, it becomes the variance of x. Okay. So what's a covariance matrix? My God, I already gave you answer here. Actually, I want to ask this question. Covariance matrix, it has the same number of rows and same number of column, okay, as the number of feature, okay. So we have two features, so we have two rows, two columns. So for the first row, first columns is correspond to good. So if you put this x as good, y as good, you will get variance of good, right? Then you put good super. So you put x as good, y as super, it will get covariance of good super. So on, just continue this super good, it will be covariance of super good. Know that the when you change the x to super of you make whether you make x to super or you make y to super, of you change the order, you make the x to good, you make y to good, it doesn't matter, right? Because this is multiplication. Whether good appear at the first element or whether good appear at the second element, it will be the same. So this covariance and this covariance will be the same. And then you have a variance of super. So this is a covariance matrix, okay? So if you calculate covariance matrix on this good and super data set, where is good and super data set? Here, let me define it. So let me calculate covariance. So these four values will capture the whole spread of the data. So all you need to, so what you need to do is you need this matrix to get a vector to do dot product, to do the dot product with the original feature, as Baron said at beginning, okay? This is our goal. So how to do that? Actually, we already finished the first step of PCA. The first step of PCA is to compute the covariance matrix, okay? Actually compute the covariance matrix of center data, but don't care about center data so far. Yeah, center data, it just means you're centering your data by mean subtraction, okay? You don't, yeah, just something like that, easy. Okay, so how you can go forward to calculate let me go to calculate this vector. The things you do is you do eigen decomposition. Sorry, I say eigenvalue decomposition. Normally we call it eigen decomposition using this covariance matrix. Okay, so what's eigen decomposition? I won't talk about the detail of mathematics. The only thing I want you to know is eigen decomposition will follow this equation. What's this equation? A is a covariance matrix. P is Covariance matrix, let me remind you, covariance matrix will capture the spread of the whole data, okay? Then this P is the vector we are looking for, okay? So this lambda, I want you guys what does this lambda mean? One hint is, this is a spread of the whole data, original data. This is also spread, but this is one value. This is value for measure what kind of spread. This is my question. Can you have guys, Feel free to write something, Baron, if you have some curiosity of Bayesian inference. This almost. I will wait for the answer for a while. What does this lambda represent? Just have a guess, have a reasonable guess. And another thing is actually related to this week past task. Yeah, related to this task. I know a lot of people will use the API like the explain variance ratio, something like that in sklearn, but do you know what exactly it is? This is this relates to the lambda here.
Lambda is a scalar.
Scalar value, yeah.
What exactly your question is? Like what you want to?
Yep. The lambda, I already told you the lambda represents, some kind of spread of data. But what this data? What spread of what this data it measure? It's measure on. Is my question. Have a guess? The P is used to transform the existing feature into new feature, right? And A is the spread of the original data. So how about lambda?
Like not I did a guess like eigenvalue because
yeah, it is called eigenvalue. Okay, so I think no one can give me variance. Yeah, Mitchell, what kind of variance? Variance is calculated on a feature. So what kind of feature? What do you mean magnitude? Oh, a magnitude is just one value, but variance is calculated on multiple value. Direction, you mean the vector, right? The P, the magnitude of P. You mean this P? This vector we are looking for? I think what you are talking about is the magnitude of this vector. I'm not sure if I'm correct. Can you give me an answer? Because I'm kind of confused. What do you mean by magnitude and direction? The magnitude of what?
Yeah, I'm not 100% sure what I mean either. I just figured it was related to the eigenvalues of the variance somehow.
Yeah. Never mind. Thank you for your answer because I need some answer. So yeah, all good. I will continue. So I will ask this question again after I continue. So let's see if anyone can give me the answer. If someone can give me answer, I'm successful tutor. Okay. Yeah. So now we have the covariance matrix. What we want is we want to get this, this vector to do the dot product with the original feature. No, let me do it. I want to do this covariance matrix. I already computed this. I do eigen decomposition. As I said, I only mention how eigen decomposition work. It's too much mathematics. Then I get eigenvector. I just hide this step. Okay, so I directly go to the eigenvector. Okay, so then we will finally we will go back to step 3, but because you can't answer me what's lambda, so it's pointless for you to look at steps 3. Okay, any?
Sorry, can I just say something? I'm not sure if correct or not. I was thinking,
Sure. Say it.
You already said eigenfactor with lambda and this scalar, and it's like a factor of the eigenvector itself. That's just it's a scalar. Represent how the eigenvector can stretch or not. That's the way I'm understanding. I'm not sure it's correct or not.
Let me think about it. You say the scale of, both lambda and p. If the p is
because if I got it right.
Sorry, just wait for a moment.
Okay.
Oh yeah. The thing is, yeah, you can consider it as scaling, but when you can consider it as scaling is when the p is determined, so you perform something on p. But here the p lambda is not determined. What we want is, okay, I have A is determined, covariance matrix. So I want to find the lambda and p which satisfies, this A. Okay.
Yeah, but it's just a value. So lambda is just a value. So
Yep.
it's a scalar as well. And
Yep.
it is in my mind, as I said, I'm not sure I'm correct. It just represent the factor or the magnitude of eigenvector itself.
The lambda itself is eigenvalue.
Yeah, but it also has a relation with eigenvector.
Eigenvector, you mean?
Yeah.
Yeah, it relates with eigenvector, but how does they relate to each other? This is question. If you can answer it, that will be great.
Yeah, just my
lambda could.
Yep.
Lambda could be a determinant of A. Like we have a square matrix, and I'm not sure how they are related, but kind of related to the determinant of A could relate to the lambda somehow.
You mean the covariance matrix could relate to the lambda somehow?
Yeah, using a determinant value. Like we have a covariance matrix A, and if we figure out the determinant of vector A, that could somehow relate to the lambda.
Yep, you are
determinant.
Correct. Yeah, I know determinant. Yeah. Yeah, because you're you are far towards the linear algebra. Just go away from that. Because I'm not sure if you can find the. Yeah, that's another process. Just don't talk about determinant for this workshop. We can talk about after this workshop, because that will make more confused. Okay, so just let me finish this vector. Okay, we need to get this vector to get the reduced dimensions so we can see results. Otherwise, Then from these results, we can see what's the lambda. Okay, so let me do the thing. So now we have two eigenvector. First eigenvector, second eigenvector. Let me copy paste this eigenvector. So this is our result. We get our result. This is vector 1. Normally in PCA, we call it principal component 1. We call it principal component 2. So let me just principal component. Okay, so let's transform this. Should I? Oh, sorry. Okay, let's transform the data now. We already get the vectors. Now we can really reduce our data. We can use this one to reduce our data into one dimension. Here is our data, right? Let me just only use principal component 1 to do dot product between them. np dot dot. Maybe I just use dot dot. Then I just principal. Then the first vector. So that is the first row, all first row, all the column, correct? So then we'll get the 4 values, right? For data point 1, data point 2, the negative review, positive review, moderate positive review, of very positive reviews. Yeah. So what we want to, before we going back to lambda, what we want to do is I want to see if the variance is really bigger than the super feature and the good feature, because that's our original goal, right? How I can do that? np.var. This is variance. Let's calculate the variance. 4.5, right? Let's see. Is it bigger than the original variance? I don't think I have original variance here, but I have original variance calculated on this figure. Good is 3.25. The super is 4.19. So yeah, we are successful. This one has much bigger variance. So all good so far. If all good, I will talk about lambda. Okay, let's go to lambda. Let me see let's see what's lambda first. I want to copy paste to the other cell where we can see lambda. Here we already have lambda, right? Let me print the, okay, I already print the lambda. I also put it here. Actually, comment it. So what's the lambda here? Let me have a look. Lambda value here is 6 for the first component. Actually, this is variance for, you know, for the transform feature, but this is called sample variance. If you remember, sample variance will divide it by n, but let me calculate the population variance, okay? Population variance will divide it by n minus 1, right? But this value has been divided by n, so let me make it back to the undivided version. So this is undivided version. I just multiply the number of feature, then I divide it again, do division again. So I use this. So this will be the population variance. Let's print out this population variance. You will see some magic here. You see, this is the result. it is equal to lambda. So now you have the answer. What's the lambda? The lambda is, if you use this P to transform the data, the lambda will be the variance of the transformed data. That's it. That's lambda. All good? Covariance. Yep.
Sorry, can you just elaborate it a little bit more? What you mean by the variance of transfer data? Data here is different data. What do you mean?
Yep. No worries. Happy to talk about this. I hope everyone would be clear. I do remember. Okay, let me go from this. Are you clear with this goal we want to achieve? We want to find a vector to do the dot product with the original feature.
Yeah.
So we can get a new feature.
Yeah.
Okay, that will be good. So let me start from this part. So what the vector we find is P, right? The eigenvector.
Yeah.
The eigenvector is also called first component in PCA, right? Let me go to that. First component of eigenvector in PCA is this one. Okay.
Correct.
So we use this eigenvector, this P, this first component to do the dot product with dot product with the original data with the original feature, the two feature good and the super to make it into one feature, right?
Yeah.
So let me just reprint this result, reprint this transform feature. So and be very, very clear. Print. I don't call it transform. I call it reduce. Actually, it's transform feature, but I think reduce will be much more clear related to the dimension reduction.
Sorry, I have a little bit of problem. I'm not strong in Python. I'm trying to get my head around. So when I try to get understand the concept by plotting and try to understand much better, I understand you calculated from the value. It's the same value. I got that. But what I ask, what's about the meaning? Why you mean here the lambda is the variance? I'm just.
You mean that's the variance actually is a variance of this transform data. You know that, right?
Okay. Yeah.
Okay, you know that. Okay. So what you want to ask is, what's the meaning of the lambda is a variance of this transform data? Why? So what it can give us? What is a usefulness? Something like that, right?
Yeah.
Yeah. The usefulness actually is related to something. I can explain it in two perspectives. First perspective is this. This equation will lead to wait a minute, eigen decomposition. This equation, there are a lot of eigenvectors that will satisfy this equation. But we want to do dimension reduction, right? We don't want to take all the dimension. Otherwise, you don't do dimension reduction. You just go back to original feature. So what you want to do is, okay, I want to choose a vector which will lead to the transform data with the maximum variance. Clear?
Yes. Yeah.
So where is the variance? The variance we can directly get from lambda by using this lambda, here I have a different eigenvector here. There are two eigenvector. So using this lambda, I can sort this eigenvector. After sorting this, the first eigenvector will promise that the transform data will have maximum variance. All good? Clear?
Yeah.
Yep. That is one important perspective. Another important perspective, you can go to the past activity. It asks you how many variants it's calculated. It's like, okay, you can know if your semantics of data, the useful information of the data can be measured by variance, by the spread of data. Then you want to know, okay, using this eigenvector T to transform the data to get one feature, how many semantics this transform feature will capture? Now you have the lambda, right? So you can use the lambda to capture the percentage of the variance. Now you can say, okay, if the percentage is 30%, 40%, you will say, okay, 30% of semantics is maintained by this transform data using this eigenvector. So this is another point why lambda is useful.
Yeah, I think I almost got what you tried to say. I think if you remember my answer, I was thinking lambda is like a scalar to eigenvector, and you're telling me here it's like a variance to data for eigenvector as well. It's related to eigenvector because most of them is like complete each other to a certain way to get the transformation. So I think I almost there. It just the variance it just came for me from the equation or from the calculation, but I'm not sure from the meaning from where it came. But it's all right. It's complex by itself.
Oh, I know what you mean now. Actually, you want to. I'm not sure. Just let me clarify. Actually, the things you are curious is, okay, why this equation will bring this lambda as a variance of the transform data? Is that your question?
Yeah, that's exactly, because I know lambda has a scale, has a value, has a magnitude, has a determinant with p. But how you get it as a variance, it just came naturally from the calculation, but I'm not sure why.
You know, my answer is I don't know. Because you need to dive into the mechanism of eigen decomposition. You know, that's the most complicated thing. That's the thing I didn't talk. Actually, that will spend the 2 lecture of 3 lecture to talk about this. A lot of mathematical stuff. If you want to dive into it,
I don't want. That's why I said it's too complex by itself, so that's fine.
Yeah. No worries, but yeah, I really would like to see someone, have some kind of curiosity to dive into this mathematics and find, that's why I think it is magic, because I don't know the mechanism, but after I look at the result, whoa, it's something like this, how it can be. So I also have such curiosity why. But then I dive into some, online to find some mathematical formula. I want to figure it out. Then I find it take too much time. Yeah, maybe in the future I will figure it out. But I don't know. Maybe when I'm 50-year-old, yeah, really need some time to understand this whole thing.
All good. Thank you.
No worries. Really happy to hear this, question. That means I'm not alone. To find let me see the variance. Maybe the use is to find a way to scale the vector data without deforming it. Eigenvector and eigenvalue essence, I think is a good resource. Yep, 3 blue, 1 brown is really good result to visualize for visualization, this vector matrix transformation. Great. But for this result, I just want to share my own experience. I think it's good to understand, one is look at, how you can think of matrix as a transformation of, let's say you have data point, then you apply matrix to this data point. What are you doing? What you do, you can visualize it as transformation of your data into another dimension, not one dimension, maybe multiple dimension. Actually, you can think that's what we do here is like dot product with principal component. Actually, this principal component, we just select one vector. But if I don't select one vector, I select the whole matrix. You can think of this is a transformation matrix. This matrix will transform this data into a different, different space. How then from through three blue, one brown, you can visualize this as the stretch of the space, how the space are stretched, how actually it's linearly transform the data using one matrix. But yeah, then you can think about it intuitively using the three blue, one brown example. That will be great. I love someone to look at this result. But yeah, but I always think, I'm not sure, but in some cases, I always think this result will make me always want to figure out all the stuff visually. Then finally, I think it's impossible. You can figure out all the stuff visually. So just make sure when you look at this result, you feel very satisfied that you can visualize this mathematical process. But don't I can't say don't try to visualize everything, but if you can, that's good. But I don't think everything can be visualized. Yeah, just my own opinions. Maybe it's not correct, or maybe I'm a lazy person. I just want to see how it works rather than visualize everything. Great. Any other problem for PCA? Because we already finished PCA. Of course, not finished. That eigen decomposition process is very complicated, maybe. But that's it from this unit.